So I'm going to start this video by asking you to read this, which is a theorem, all right, that I just underlined, in symbols for W, such that f of A, or W lies between f of A and f of B. There exists a C, such that C lies between A and B, such that f of C equals W. Okay, how many of you read that and say, oh yeah, I get it, that makes perfect sense, right? Probably to most of you, if you've ever watched the Peanuts, Charlie Brown, I sound like the teacher in Charlie Brown, right? Want, 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 right? When I read you that theorem. Our goal, though, is for you to be able to understand that even though a theorem can sound and look complicated with all these symbols, this is actually a very easy theorem. It's the must-could thing that we did the class before. Okay, so if you look above in plain English, this is going to make sense, and this is what most of you wrote on your paper. Okay, if f is continuous on this interval, at some point, f must take on, and so that's the function, right? That's the y value. So I believe the first example, so again, we didn't know where A was, we didn't know where B was, we just knew they were values of x. And I had said this was at -3 and this was at 5. You realize that every must was in between -3 and 5. Everything else was a could, okay? Because we didn't know what the function was doing. We just knew it had to connect point A and B with a continuous function. So to help you understand the in symbols part, so say that the function connected A and B like that, okay? And I came along and I put W right here, okay? So W has to fall in between, so this is f of A right here, this purple dot, f of A, and this purple dot, f of B. W has to fall in between there. And what it says is there has to be a C such that f of C, right? So if I go over here, so W is a y value, there has to be a value C on the x-axis in between A and B, such that the functional value at C is W. Okay, and that has to happen no matter what the function looks like connecting points A and B. All right, so here's one illustration. Let me just draw you another illustration because again, we have no idea what that function's doing. Okay, so that function could have done something like that. Okay, we have no idea. And I can put my W anywhere. Okay, so maybe I'll put it down here and then I'll go across and see that my W still lies between the -3 and the 5. There has to be a C, right? It happens right here. There could be more than one value that would output W, but there has to be a value of C such that the functional value of C is W. Now this theorem, which is so simple, all of you figured it out very simply, has some important consequences. And here's one of the most important consequences. So in your notes, this is called the intermediate value theorem. In your notes, you should write that as your heading, and you should write the plain English definition at least. Okay, but if you want to understand, put the symbols, go for it. Our goal, like I said, is for you to understand that behind these complicated symbols is often a simple idea. Now, here's a really important consequence. When the functional values have opposite signs and the function is continuous, then there has to be a 0 on that interval. Okay, and so we know we're always interested in finding zeros. One of the ways that that's going to be very useful is when we're working with polynomials, okay, and we love polynomials. They're these nice, smooth curves. They have no asymptote lines, no holes. This would be an odd degree polynomial, okay, I can tell by the end behavior. But later in the course, we're going to start looking at slope. And if I came over here and I noticed that the slope was positive right here, okay? And then I came over here and I noticed that the slope is negative. Let me write negative. The slope is negative over here. What that tells me then is there had to have been a point where the slope was 0, okay? Well, what kind of line has a slope of 0? We know that that's a horizontal line, and we know that at turning points, right, if I drew what's called a tangent line to the curve, this line at a turning point would have a slope of 0. Okay, then I'd come back over here, so I'd look over here and say, okay, slope's negative here. Now the slope's positive over here again, and that would help me determine, okay, then there must have been another point in between here where the slope of the curve is 0. And again, that's helping me see that I would have another turning point. So this is going to be an extremely important consequence of this simple theorem. So what you need to do right now to prove that you watched this is just do exercises 1 and 2. You can put them in as text or as a PDF. There still is one more video to watch though for today, so stay tuned for that. Thanks for watching.